We now know how to implement all four types of control sources using a MOS transistor. The MOS transistor by itself is a voltage controlled current source whose proportionality constant is Gm, the transconductance, and all these control sources behave ideally if this Gm, which is used to realize the control sources, tends to infinity. Okay, now we'll see how we can realize such control sources when the basic device that we have is a voltage controlled voltage source. Okay, a MOS transistor, as we know, it's a voltage controlled current source. The current is Gm times VGS, where VGS is the gate source voltage. Now imagine that instead of this voltage controlled current source, we had a voltage controlled voltage source to begin with. Okay, and let me say that the model looks something like this. There is a voltage VD between these two terminals. I'll call them plus and minus, and one side of the control source is connected to ground, the other side is the output. Okay, this is a voltage controlled voltage source with some restrictions. This one side is connected to ground and so on. So now instead of using the MOS transistor, we can try to use this basic device and implement our control sources using negative feedback. Okay, so that is, we will implement a voltage controlled voltage source and a current controlled voltage source using negative feedback and this particular device. Okay, now this is already a voltage controlled voltage source. You may be asking why I need to implement voltage controlled voltage source using negative feedback around this one. It's exactly the same as why we implemented a voltage controlled current source using the MOS transistor when it's by itself a voltage controlled current source. The point was the following: Gm of the transistor, which is the parameter of an active semiconductor device, it varies substantially with temperature. It varies from MOS transistor to MOS transistor, whereas the voltage controlled current source we realized using this had a transconductance which was defined by a resistance, okay, which can be much more accurately set. Similarly here, this A0, when it's realized using a semiconductor device, can vary widely. We want to have a voltage controlled voltage source whose gain is determined by not a semiconductor device but something like a resistor. Okay, so we will try to do this. Now of course I don't need to make this any more mysterious than it is. You know what this is the model of. It is the model of what is a very popular device, the operational amplifier or the op-amp. Okay, this is the output, this is the plus terminal, and this is the minus terminal. So essentially what I'm saying is, we will try to realize the voltage controlled voltage source and current controlled voltage source using an op-amp in negative feedback. Okay, so first let's consider the voltage controlled voltage source. The output voltage V0 should be equal to K times the input voltage, where K is some gain. In other words, now for us to realize this using negative feedback, we have to define some error, and based on that error we have to drive the output up or down. Now what does our op-amp do? This voltage is Vd and the output is some A0 times Vd. So if this voltage is small, or if it becomes negative, it drives the output also negative, and if this input voltage is large, it drives the output to large positive values. Okay, so what we have to do is, we have to define some error between desired and actual quantities and feed it to the input of the op-amp in the correct sense, such that the output is driven to the desired value. Okay, so what is the error? The desired quantity is K times Vi, and the actual quantity is V naught. So we can define the error presumably as kVi minus V naught. Okay. So that is the op-amp's input voltage. The op-amp reacts to the input voltage, right? So its input voltage should be related to this error. But this clearly has a problem. Okay. Where do we get kVi from? That's in fact what we are trying to find. Okay. If we already had kVi, we won't be building this amplifier in the first place. But exactly the same information can be had by dividing this entire quantity by k. So I'll redefine the error as Vi minus V naught by k. Now you can clearly see that if the output voltage is smaller than required, then this error will be positive. Okay. And if the output voltage is much more than required, then this error will be negative. Okay. Now this is okay. We don't need kVi, we just need Vi, which is the input voltage, which of course is available. Okay. Now what should happen is that if Vi minus V naught by k is positive, output must be increased, and if Vi minus V naught by k is negative, the output must be decreased. And what does the op-amp do? If Vd is positive, the output is large and positive, and the more positive Vd becomes, the higher the output voltage will be. It will increase the output voltage. That is, positive values of Vd will tend to increase the output voltage, and negative values of Vd will reduce the output voltage to large negative values. So it's clear that this Vi minus V naught by k should be the difference voltage of the op-amp, the input voltage of the op-amp. Okay. In order to be able to implement this, we need V naught by k, where of course k is more than 1 because this is an amplifier, and that's very easy to obtain. Okay. How do we obtain 1 by k times V naught? If we have V naught here, so let's say we have V naught there, we can obtain V naught by k by having a resistive divider of this ratio k minus 1 r and r. Okay. So this gives me V naught by k, and I have my input source Vi. The op-amp has two input terminals. Okay. So if I connect Vi to one of them and V naught by k to the other, we get Vi minus V naught by k. Okay. So this does appear to be in the correct direction. If Vi is more than V naught by k, then this positive value will drive up the output of the op-amp, and similarly if Vi is less than V naught by k, the negative value will drive down the output of the op-amp exactly as you want. Okay. So now we need to insert the model of the op-amp, which is a voltage controlled voltage source, and see what exactly the output voltage will be. Okay. If you do that, this is Vd, and you know that the model for the op-amp is A0 times Vd. Okay. So V0 is A0 times Vd, or Vd is V0 by A0. So this number here is V0 by A0. Now all I need to do is to write one equation. This voltage is Vi, this voltage is V0 by A0, and this voltage is V0 by K. So Vi minus V0 by A0 equals V0 by K. Okay. So it's very easy to see that V0 by Vi equals 1 by A0 plus 1 by K. It can also be written as K by 1 plus K by A0, and it can also be written as A0 by 1 plus A0 by K, and so on. Okay. If you are familiar with op-amp circuits, you would have probably seen all these forms. I will use this form, and in this you have K, the desired gain in the numerator, and something in the denominator, and you can see that the denominator approaches 1 if this K by A naught goes to 0, okay, or A naught goes to infinity. So V naught by Vi is approximately K if A naught by K is very large. Okay, so this circuit here, using an op-amp which we model as a voltage controlled voltage source, and that's how it is conventionally modeled frequently. We can divide the output voltage using a resistive divider, and the input is compared to the divided voltage, and the output is driven based on the comparison. Okay, so that's Vd, that's Vi. And if the op-amp's gain is A naught, that is, if the voltage controlled voltage source inside the op-amp has a gain A naught, then V naught by Vi equals K divided by 1 plus K by A naught, and this will be approximately K if A naught by K is much more than 1. Essentially, A naught, the gain of the op-amp, has to be very, very large. Okay. Now this of course is probably familiar to you, and also I am going rather quickly through this because this is treated in courses like basic electrical circuits. If you're not familiar with this, please go back to those lectures and brush up yourself. The bottom line is we can realize a negative feedback amplifier, negative feedback voltage controlled voltage source using an op-amp, which is by itself a voltage controlled voltage source. But the important thing here is that even if A naught changes by some amount, okay, let's take an example where K equals 10 and let's say A naught equals 1000, then V naught by Vi will be 10 divided by 1 plus 10 by 1000, okay, which approximately is 10 times 0.99 or 9.9. And let's say A naught changes to 2000. What happens then? Instead of this 1000 here, you have 2000, and instead of this 0.99, you will get 0.995. So the gain becomes 9.95. Okay. So this is the advantage of negative feedback. You may be wondering why I realized a negative feedback controlled voltage source using an op-amp, which is by itself a voltage controlled voltage source. This is the reason. The parameter of the voltage controlled voltage source within the op-amp, the gain of the op-amp, can vary by quite a bit. It can vary by a factor of 2. But you can see that V naught by Vi, the closed loop ratio of the voltage controlled voltage source, is changing from 9.9 to 9.95. It's changing very little. So negative feedback circuits have this advantage of having low sensitivity to amplifier parameters, and amplifier parameters tend to vary a lot because they are based on semiconductor devices. So if you realize these things using negative feedback, you can have very well controlled parameters. That's the idea. Okay. So this is a voltage controlled voltage source using an op-amp.